and welcome back. Is this fun? As we're going through this series of lectures, we're kind of revealing the onion, revealing the abstraction layer, and we're explaining how really the system works. So now I understand how to play with memory, how to request it with malloc, how to give it back in free. Really cool. But there's some more details to this. So let's actually take a reflection of where do things really live. This is really neat. People have never seen this before. You don't know this on your own. If you just pick up C on your own, you could be programmed, say, 100 years, but you wouldn't know the things unless you get told this. I always read the book and probably tell you, but people don't read the book. But if you just kind of pick it up on your own, you're not going to do it. So, don't forget global variables, first of all. So, let's just summarize. When you make a structure declaration, that just declares a new type. A structure. That doesn't make any space for it. That's just kind of here's a new type I'm going to use. But when you make a variable declaration, that actually does reserve memory. So that the first one doesn't, the second one does reserve memory. So far we talked about several ways to allocate memory for data. You can have a local variable, int I, struct node list, that's the node, two fields, value and next, character star string, that's the space for the pointer, but not for the string itself. Int AR of n, there's n integers, got that. Or dynamically, pointer equals struct node star, malloc, size of struct node times n. That's n nodes in a row. There's an array of nodes rather than a linked list. There's an array of those nodes. That's pretty cool, of those struct nodes, I should say. There's one more place. So one way is a local variable. The second is this malloc-y thing. You don't even know where they live yet. I'll tell you that in a couple slides. And then finally, you could have a global variable. If I say int global, int my global here, above main, so main is your top level procedure always in C. But if I put my global above main, it's now in the global namespace. You now have access to my global everywhere. Any subroutine, including main or sub or foo, has access to read and write my global. That's pretty cool. So if you need to have some value that's going to be shared, rather than passing it here, just this thing that's there, just out there. Now, don't overuse it. You could obviously write the worst code in the world by having a billion globals. But if you have some constant, like a big table or something, you can use that without having so gross code. Although probably it's better to pass things around. But you can still, small programs use globals sparingly. So use them sparingly, and you'll be fine. Has global scope. So now, let's use some words. Use your words. C has 3 pools of memory. Okay, remember I had these local guys, I had this malloc guy, I had this global guy. Turns out that they live in 3 different places. The first one, static storage. That's the global space, it's static. Static means it doesn't dynamic, it's not dynamic. It means it's frozen, doesn't mean you can't change it, but it means it can't change the size of it. You can still change the values inside, like my global can be read and written to, but that lives in the static. So global variables live there. Permanent and there for the whole program. So it's not going to grow, okay? So static doesn't move. The stack is where your local values are. You might have heard the stack. Stack Overflow, you've ever heard? Oh, maybe. Let me find something on Stack Overflow. Now you know Stack Overflow. We'll talk about why the stacks overflow. But you got a stack. Local variable storage, parameters, return addresses. All these things are in the stack. And the heap is where your malloc goes. So dynamic stuff is the heap. I need to apologize on the basis of all computer scientists because the stack, the name stack, is the same as 61B's, a stack data structure. And in fact, they operate very much the same way, okay? So they're the same, kind of the idea of the stack in memory and what a stack is, same thing. The heap is not the same as the heap data structure. So I apologize on the basis of all computer scientists who went before me because it's a terrible name. The heap is not what a heap is. It's not stored, it's not somehow represented using a heap. It's not. A heap is just a heap of memory, okay? Don't think of the heap, oh, it must be stored like a heap structure. It's not, okay? Stack is stored like a stack, operates like a stack. The heap is not, okay? C, really fluent C requires you to know what those 3 things are. This is why I think teaching C to CS1 students, to intro programmers, is a terrible idea. It's just too much to learn about how the machine works and how the code works and how to debug. Too much. Easier language, Python, blocks-based language, something else. But don't teach in C initially. Third language is fine. Now you know how to program, but now you learn how to program well. So here's a picture. The address space contains 4 regions. This is pretty cool. I love this picture. Finally, I'm looking like, revealing open the hood. There's light shining out of this. Okay, the stack, local variables, remember? It starts at the top. Remember, roughly, you have access to 32-bit machine, 2 to the 32, 0 to 2 to the 32 minus 32 minus 1 bytes that you can read and write, okay, for now. Stack starts at the top and grows down. Phew. So as you have more things, as you increase the stack, it's going to go down towards 0. The heap grows up towards this middle space. Static data is locked in. You know what the size of it is. It's locked in. And in fact, the code, when you run a program, if I run foo, I run some program I've run, hello world, the code for that gets loaded into memory as well. So that memory footprint contains all the code, all the static space you have, all those globals, any heap you've requested, probably nothing initially, and then whatever stack has initially, probably is main information here, like maybe the arguments passed in are up here, okay? Why do we like this model? Well, it's nice because if I had a program that had a lot of stack, I had a lot of stack users but little heap, can you give me an example like that? What might it be? Well, no heap means I never call malloc. A lot of stack means maybe a really long recursive, maybe a runaway recursion, maybe a big fractal, or maybe I'm doing factorial of some huge number. Calls this, because those local variables, all those function calls grow the stack. Okay? We'll talk about this. We're going to explain that a little bit more in a couple slides. How about heap? Can you think of something where the heap grows up and almost no stack? Well, no function calls, so stack is going to grow, really. No arrays up there. Remember, no temporary variables that I'm used in main, so the stack is pretty small. And I have, the first line is a massive call to malloc. Zoop, now the heap would grow up high. Do you know what program would allow you to have almost direct control of malloc? Photoshop. I want a new document. I want it 1 million pixels by 1 million pixels. That's, no, maybe 1,000 by 1,000. That's 1 million pixels. And now it has to grab it somewhere dynamically. Grabs it from the heap. Another difference between the heap and stack is, AR square brackets, that's nice, except that you can't, if I say AR of 1 million, what if I don't have room for 1 million? It'll crash. But if I ask it through malloc, what'll malloc return? Null. So you can now have code that is resilient to memory failure if you use it malloc versus using arrays. We'll talk about more, but that's kind of an example. Like arrays are really fast. I can get it really fast. Malloc might take a little bit longer. We'll get to this in a moment as well. But malloc has the ability to tell you if it can't get it for you, where the array, if you want to make a million array, maybe there isn't room at all. Maybe you've heaped a lot and now there's no room here, but it would crash if you say, local variable, open square bracket 1 million. It can't get it. Crash. There's no way to catch it. There's no way to save it. Codes at the bottom, static data, heap, and the stack. Okay? Important. And now, but for now, don't worry about how somebody prevents them from over crossing each other. Okay? So somehow that's prevented. The OS will handle it. Take 162 to learn all about it. So where are they allocated? I've kind of told you before. If they're declared outside a procedure, meaning outside of all procedures, my global, they're in the static area. If they're local, they're on the stack. If they are in malloc, they're on the heap. I said this before. And by the way, malloc is a procedure. Now, let's talk about what happens. They're free with the procedure returns, which means, wait, so foo calls bar, and I get some local temporary space. When bar goes away, it's actually freed now. All that stuff that bar had, all those local variables that bar had, all those arrays that bar had, that are not malloc calls, but arrays, they go away when bar returns. So that's actually kind of cool. And main is a procedure as well. Here's your stack. Let's go a little deeper on the stack. So the stack frame includes the return address. So how to go back to the previous guy, important. Any parameters you have, and space for any local variables. So if you ever, like foo calls bar, calls baz, you ever wonder, how does it know where to come back to? It's the stack. That's how it does it. The other key thing is the stack is a contiguous block of memory. You'll see that malloc can actually be all over the place. It can be here and there, and that's going to be a problem. But the stack is always continuous. It grows like a stack. Unlike a stack, it grows down. Normally a stack grows up. When you think of it, this stack is growing down, okay? And the procedure ends, the stack frame is tossed off. So it frees it dynamically. Pretty cool. So let's actually take a look at this. Let's make a little animation. So I'm in main, okay? Got some space for main. Some local stuff is going on in main. I'm happy. I call A of 0. I got to know where to come back to. So I got to somehow set up, I have to somehow set up a structure where I need to know when A returns how to come back to me. So I have to store the line after A0, the line right here. This is the key thing, right there. That address, that address in the program needs to be stored somewhere. So when A comes back, I reload. That's where I'm going to start from. Someone's got to remember that, and it's the stack. That's the key. So, whoops, let me erase this here. Okay. All right. So now I call A. That's the bottom of the stack pointer, okay? I'm going to now make a function call. So I'm going to grow the stack. I'm going to store my return address and any temporary, I'm going to pass in any parameters. Here we go. And I've now grown the stack, and now that's where A is. So now main and A are alive, and the stack now has both of those active. And so any temporary variables that are A are in that area, and that's the blue. I try to color code them the same so you can kind of see the same, okay? Well, now A is going to call B. So I better grow the stack, move the stack pointer down, okay? By the way, that's really fast, okay? To do this, I basically take a stack pointer internally. I'll tell you, when we learn about assembly, you'll learn about this. I just move the stack pointer down. It's really fast, okay? To grow the stack is very, very fast. And to shrink the stack, just move the stack pointer up. Pretty easy, okay? All this is now the room for B's local variables. Any parameters, the n has got to be there somewhere. All those things are there. Turns out that the n actually gets passed as a register. Too much detail now, but some space for B to work with, okay? And to know how to get back to A. Then I go down to C. Same thing. All we're doing is the same thing. And I go down to D. Now here's the key. I'm going to now invert this. Now D returns. So watch what happens. Did I go back into the code and erase it? Grab my eraser and erase the memory to make it all zeros? No, the answer is always no. I don't have time. No time, no time. It's almost like no time, no time. It's like my joke about ain't no free lunch. No time, no time. I'm too busy. I can't erase it. So you're going to notice, interestingly, that if D had some secret value, password up to the whole world's computer system equals Bosco, and you typed it in the local variable. So it lived in here. Somewhere in here was Bosco. And now, that was when the stack pointer was there. And now I return from D, and I go back. Well, guess what? Like the PowerPoint shows you, it's still there. Even though I don't have access to it, officially I can't be accessing anything past the stack, Bosco is still in memory. Interesting, you should check that out. It's really fun. So now, let me clear that up. Now C returns. I just move the stack pointer up, and immediately that space isn't zeroed out, but is not space I can use anymore. Okay, now B returns, and A returns, and I'm still in main doing my stuff. Isn't that cool? So that's basically how that, notice that was like a stack. A stack goes down, stack goes up when you function called and you return D to C to B to A, back into main. Now we're living here, and now main is working with all its local variables, doing all the right thing. It's pretty cool. And it knew how to get back because you had the stack. The stack was, again, we learned this all when you learn about assembly. You need to know how to come back, all that's stored in the stack, all the local space is there, and you free it by moving the stack down and moving the stack up. Easy. See you at the next lecture.